Thanks. So what I want to talk about is primarily the link between global temperature changes and global sea level. And I will start with an image that John Schellenhuber already showed yesterday, and that is the very long-term paleoclimatic perspective about how global temperature has been linked to sea level in the past. And you can see, John explained all that already, that there have always been very large sea level changes associated with relatively modest global temperature changes in the Earth history. For example, at the height of the last ice age 20,000 years ago, the global temperature was only about 5 or 6 degrees colder than now, yet sea level was 120 meters lower. And if we go back a little further in time, if we go back 3 million years, that's the last time the Earth was noticeably warmer than at present, about 2 or 3 degrees warmer. Sea level was about 25 to 35 meters higher. Those big sea level changes, of course, come from the ice sheets. And that is also the reason why the projection that we have for the future, does this laser pointer work? Yeah. Here of, just as an order of magnitude, about a meter of sea level rise by 2100 for something like maybe 3 degrees warming or so, looks kind of really off the line. The reason, of course, is that 100 years is a very short time, and you will only see the small beginnings of the sea level response over the first 100 years after this warming has started. So I really want to emphasize that in the longer run, we are expecting really big sea level changes from the climate changes that we are causing now. So now, of course, we are in the middle of a global warming. I just show the temperature record here. Once again, you're all familiar with that. This is a NASA GIS data, and just as a little aside, if you just take the first 8 months of this year, for which we have the data in, the average is kind of back onto this long-term trend line. So 2008 was just a year that happens to be below the trend, like you always have some individual years below the trend, and you have some that are above the trend. Nothing special about it. I mention it because the BBC, I think it was, who last night again thought it was worth discussing whether there was any global cooling in recent years, which is, of course, nonsense. It's entirely consistent, the temperature record, with ongoing global warming plus natural variability. But that's not what I want to focus about. I want to focus on how this warming is linked to sea level. And of course, we also have sea level data going back about a bit more than 100 years, about 130 years, from tide gauges around the world. This is the famous Church and White tide gauge data set shown in red here, which has also been adopted in the IPCC report. And since 1993, we have satellite data, which are added on here at the end, and during the period of overlap, of course, they agree quite nicely with the tide gauge data. What you can see on this diagram is that, first of all, sea level has risen about 20 centimeters. Oops, I didn't want to go further. 20 centimeters in the past century or so. You can also see by eye that the rate of rise has accelerated. You don't need fancy statistics for that. I just drew in the diagonal line here, and you can see in the beginning it's flatter, and at the end it's steeper than that, and I will come back to that acceleration in a minute. And in terms of impacts, just as a reminder, I put a picture of the Sizewell B nuclear power station here to remind people that there is a lot of very vulnerable, sensitive infrastructure right along our coasts, including many nuclear power stations, because they take the seawater as cooling water. Now, this rise in sea level is faster than expected in our models. Here we published in 2007 a comparison for the TAR models, but it also holds exactly the same for the AR4 models, which don't show any significantly different sea level projections compared to the third assessment report. And we can see that the observed rise here in the satellite altimeter has a linear trend of 3.4 millimeters per year. The best estimate of the TAR is shown in the middle here. These are the different emission scenarios. They are, for that short time period, they're all pretty well on top of each other. Best estimate is 1.9 millimeter per year, so the actual rise is about 80% faster than what the models have projected. So things are worse than expected on the sea level front, or maybe they're also much better than expected. For example, you could read this in the newspaper. Over the past 2 years, sea levels have not increased at all. Actually, they show a slight drop. Should we not be told that this is much better than expected? Of course, there's not many people who talk rubbish like that. One of them is Björn Lomborg, who wrote this. But unfortunately, there are always media who really lap this kind of thing up and like to publish it because it's controversial. I particularly like the title of this article by Björn Lomborg, "Let the Data Speak for Itself." Of course, he didn't show those data. Otherwise, his readers would have seen through the trick quite easily. He was referring to this 2-year period here, and in a noisy time series, you can, of course, always pick a sufficiently short period that shows any trend that you like. This has nothing to do with science, of course. So back to Science, in this case Science Magazine. Here we published an article, or I did 2 years ago, which was an attempt, given that we know the models are not doing so well, to estimate sea level in an empirical way, learning from the data from the past 120 years, and just see how does the observed sea level rise correlate with global temperature. And I literally dreamt this up overnight. I thought, I'm a physicist, what is the first order response that I expect? And as argued in this paper, the first order response that I would expect is that the rate of sea level rise, here the time derivative of the sea level, should be proportional to the warming above some previous equilibrium level where sea level was in equilibrium with temperature. And so I went back the next morning to the data that I had on my laptop and see whether this idea works, and surprisingly it does. The rate of sea level rise, which is the red curve here, derived from the Church and White tide gauge data set, shows quite a similar curve as the global mean temperature. So indeed, these two things are roughly proportional. So to first order, that idea works. And I will refer to the old model, because we have been thinking about some refinements of this idea. And this is a refinement that was proposed by my colleague Martin Vermeer. And it simply adds here another term, a fast response term, where the rate of sea level rise is proportional to the rate of temperature change. So sea level is directly proportional to temperature. This is what you expect, for example, for the thermal expansion of the ocean mixed layer, which responds very rapidly to warming. So you get some component of a pretty well immediate response. And adding, of course, that's physically a good idea, a well-based idea, but then you have to test it with data, whether that actually works. And we tested, because it's a fast response, we tested this on synthetic data from a climate model, from a coupled GCM, which are shown here in the red curve for the past millennium. And these excursions here of the rate of sea level rise, this is due to volcanic eruptions. So you see some pretty rapid responses here in the rate of sea level rise. And the blue curve shows what that very simple equation here that I showed here at the bottom would give you. And this equation has been calibrated only to 1880 to 2000, so calibrated to this last period. And you can see that it does extremely well over the previous millennium here as well, in contrast to the old model that doesn't have the fast response term, that is that gray curve here, and that's of course unable to follow these very rapid wiggles. Now that's only for thermal expansion. That's all we can test in climate model data, because they only do thermal expansion reliably. The other thing is to look at the observed data, and there we made a second refinement to the Church and White tide gauge data set, because in 2008 this data set of the amount of water stored in artificial reservoirs was published in Science. And so we included that effect, because it is actually quite significant, this water storage. It has taken away about 3 centimeters of the global sea level. That's how much water we have in artificial reservoirs. And you have to add that back in if you only want to look at the climatic effect on the sea level. So we went to this red corrected tide gauge time series, which then, of course, translates also into higher future projections, because the climatic part of sea level rise in the last century also is a bit higher if you account for this. So with these two modifications, how does it compare with the observed rate of sea level rise? Here again in the red curve we have the observed rate of rise, and the blue curve now is that new model with the adjusted data, including that reservoir adjustment and with the second fast response term. And you can see, compared to the old model that I published in 2007, the fit is greatly improved. What that is mainly telling us is that the misfit we had between the observed rate of rise and what the simple model produced, that misfit is largely proportional to dt by dt, which is the extra term that we added. And that's why when we add that term in, the misfit basically vanishes and we get an, well, pretty close to perfect fit here. Now, from that, of course, you can ask, how will this continue? We see that the rate of sea level rise has risen very much as temperature has gone up. And if you believe that as temperatures will continue to go up, the rate of sea level rise will also continue to go up in the future, then you're with me. If you believe that the rate of sea level rise will suddenly stop increasing and will stay constant for the next 100 years, then you're with the IPCC. I will show that but before I show that, I want to show how this rate of rise translates into actual sea level. So this is in red the Church and White tide gauge curve. The annual values are also shown here, and in blue is a prediction from that simple model. And you can see that we get a very good fit to the past sea level data. Here the difference is everywhere less than 7 millimeters, and we explain 98% of the variance with this. So what happens if we plug in future projections? We take the IPCC temperature projections because we think those are reliable. Temperature is something that the climate models do very well. It's simply based on a global radiation budget, which we understand very well. And here we have all those different scenarios that we already discussed several times here during this conference. And you can see in those ranges the sea level projections that we get for those scenarios, assuming we put in a big ensemble taken from the IPCC report of simple model emulations of the GCM ensemble. So we have a full set of different climate sensitivities, etc., that are spanned by the IPCC climate models here. And all these scenarios, there are so hundreds of different scenarios went into this. And they're shown here the average value for each emission scenario and the spread. And the gray area, that is an additional uncertainty due to the quality of the empirical fit here. And overall, if you like, the full range that we expect is between 75 centimeters and 1 meter 90 by the year 2100, above the 1990 level. And that's why I said you're with IPCC if you think the rate remains constant from now on, because if you take a satellite altimetry rate of 3.4 millimeters per year and assume it's constant, you just end up in the middle of what the AR4 projected for the year 2100. The main reason in terms of physics, by the way, for that is that the AR4 assumed that Antarctica would gain ice and even would gain more ice than Greenland loses. So the net contribution of the big ice sheets in those AR4 projections is on average negative. And I don't think personally that that's a very realistic assumption. Now, if we're talking about 4-degree conference here, I picked out the range that I get 4 warming scenarios that are pretty well exactly 4 degrees by the year 2100, and then you end up somewhere between 1 meter and 1 meter 30 above the 1990 level. By the way, this is 4 degrees above pre-industrial, which I chose here, since when we're talking about the 2-degree policy target, it's defined above pre-industrial levels. So these 4 degrees, this is like 3.2 degrees above the present day. So my conclusion would be that a 4-degree world is going to end up very likely with more than 1 meter sea level rise by the year 2100. Now I want to finish off with a slide that Pia already just showed, with a range of future projections, including some for the more longer term, because I want to get back to emphasizing the fact that sea level rise does not stop in the year 2100. It will continue even if we stabilize temperatures. And that was actually the point of that German Advisory Council for Global Change estimate that I'm one of the co-authors of. The point here was to emphasize that we are committing the world by our decisions in the next decades to a sea level rise, which will be very large in the long run, over hundreds of years, because there is simply no way I can see that you could stop this rise, even if we have gone to zero emissions. If we go to zero emissions, we will roughly stabilize temperatures. They're not going to go down very much, even in a zero emissions world. That's something that, for example, Susan Solomon showed quite clearly in a PNAS paper recently. And if the temperatures stay up, and here we assume they are stabilized at 3 degrees above pre-industrial, if the temperatures stay high, then sea level will keep going up at a certain rate. And yesterday here we discussed whether we lose control of the climate system once we go to 4 degrees or so. I think that even if we go to 2 degrees or 3 degrees, we certainly will lose control over our sea level rise, because there is basically nothing we can do to stop the sea level from rising once we have caused this warming, unless we manage to cool down the planet, cool it back down again. But that would actually require extracting the CO2 again from the atmosphere, which I don't think is very feasible. At least no known way of doing this on a sufficient scale is known today. So to come to my conclusions, first of all, sea level is rising. It's a measured fact. It has risen 20 centimeters since 1880, and this is also, by the way, a modern phenomenon. It's not something that has been going on for centuries before that. This is a recent thing that is explained by the 20th century global warming. Since 1993, since we have the satellite data, the rate is 3.4 millimeters per year. So we do see an acceleration over the 20th century here. And the future rise does remain rather uncertain. That's very clear. We don't really have reliable models. And also the semi-empirical approach that I proposed here is, of course, although it works for the past, there is no way of knowing how well this will continue to work into the future. I'm not claiming that this is the reliable method of projecting sea level rise. Although if I think about the uncertainties of this, I would put more than 50% bet of this semi-empirical approach underestimating the future rise rather than overestimating it, because there are some mechanisms of non-linearity, especially in the big ice sheets, that you can think of that would make this simple linear assumption an underestimate. But this semi-empirical approach will give you more than 1 meter at 4 degrees global warming above pre-industrial by the year 2100. But as I said, in the end, it's not going to stop then. Over several centuries, we will see several meters of sea level rise, and I'd be really interested how the Dutch will keep up if we're not 1 meter but 2 meters or 3 meters, and how those cost estimates hold up, whether a 2 meter rise causes double the cost as a 1 meter rise, or whether there's a hugely disproportionate increase in the cost then, and maybe in the discussion later on we can touch on those issues. So a little advertisement at the end. If you want to read a lot more, I recently published a book together with Catherine Richardson, which, among other ocean issues, covers the sea level problem in quite a lot more detail than I could do it here today. Thank you.